Okay, good afternoon, everyone. It's my turn to introduce this week's seminar. So for those of you who don't know me, I'm Jerry Bartholomew. I'm a professor in the microbiology department here at OSU, and I'm an organizer of the OSU Art Sci group. Earlier this year, my co-host, Dominique, who it sounds like everybody knows here, she organized a series of talks by scientists on the positive aspects of climate change in order to inspire artists to submit an art piece to a fall show at the Corvallis Art Center entitled, "What Will Nature Do?" So we are continuing this term with a series of talks that is co-sponsored by the Art Sci Group, the Corvallis Art Center, and the Department of Biological and Ecological Engineering, which features scientists who are also artists or artists who are also scientists or have a scientific background or interest, with the goal of exploring how their science might inform their art, how their art might inform their science, and how they integrate these two disciplines. And so today, we're really fortunate to have two speakers. I think Leah Wilson will be leading off, and Leah is a visual artist and writer who lives and works in Eugene, Oregon. She's had a very full past, but I'm going to summarize it here. After earning a Master of Fine Arts degree from the San Francisco Art Institute, Leah pursued her art and whitewater kayaking in the Sierra Nevada foothills. Through this overlap in interests, she created a pivotal project influenced by the environmental decision-making processes of scientists, resource managers, and special interest groups during the FERC relicensing of the South Yuba River. Then in 2012, an artist residency at the H.J. Andrews Experimental Forest in the Oregon Cascades introduced her to ecologists working on long-term studies in the forest. She was attracted by the long-term focus of studies and is now an episodic, and we'll call it a lifetime artist in residence at the Andrews Forest. And the place and the scientists that she collaborates with continue to shape and influence her work. One example of the work that has come from these collaborations is Listening to the Forest, which was installed last year in the new George W. Peavy Forest Science Center as part of Oregon's Percent for Arts program. And I know that we aren't on campus very much right now, but if you get a chance to go in Peavy Arboretum, into Peavy building, it's really worth checking that out. And it's not hard to find. It's back by the stairwell. So if you climb the stairs, you'll be looking at it front and center. Our other speaker, Steve Wondzell, is a research ecologist in the U.S. Forest Service's Pacific Northwest Research Station. After studying plant community dynamics in the semi-arid desert grasslands of Big Bend National Park in Texas, he moved to the Pacific Northwest in 1988 to work at the H.J. Andrews LTER. So here's our first overlap. Among the many research projects he's worked on, he studies how hydrology and channel morphology control small-scale stream groundwater interactions and the way that these influence stream ecosystem processes, especially thermal regimes and the cycling of carbon and nitrogen. And earlier this year, he gave a talk on the influence of climate change and channel restoration on stream thermal regimes for the Art Center show. So with that introduction, I'll hand things over to Leah.
Thanks, Jerry. Let me just get the right thing here to share. Okay. Okay, can you see the presentation okay?
Yep.
Okay,
Looks great.
excellent. Yeah, good. So hello, everybody. Thank you so much for joining us today. It is really a beautiful day out there. So I'll be providing some context for just a few of my projects that have been influenced by field research. And then Steve is going to broaden the context for some of them from his perspective, stemming from his work as a hydrologist. So my intention for our time is to create the opportunity for an art science conversation. And we do encourage you to join in the conversation too. I create artwork in a variety of media, but my roots are with drawing and painting. I often work at the intersection of art and science, but my work does not clarify, explain, or illustrate science. It doesn't offer any answers. If anything, it leaves the door open for more questions. I'm a place-specific visual artist, which means that I respond to and I interact with specific places over a period of time. The place is the foundation of the work. It sets the boundaries and it often calls the shots. Time holds meaning. Time and place are my collaborators, not my subjects. All of my projects are created with the purpose of developing a deeper relationship to the place by orienting myself to it physically, as well as embedding it in my memory. In essence, I'm trying to know a place as intimately as I can through time by the process of making art. Landscape painting and photography mostly show how a landscape appears in a single instance of time, but that really doesn't give a good impression of the place. Images like this freeze the landscape and hold it captive. Instead, place is intertwined with time. Landscapes are ecosystems in fluid motion. They're never static. The only way to be true to the story of the land is to pay attention to the way that it sways through time. Time is like a metronome that keeps the beat for the rhythm of a place. Without time, there's no rhythm, there's no music of the land. And we feel this rhythm within us when we feel we know a place, and the rhythm becomes a part of us. However, it's not as simple as that. There isn't just one set of time that keeps the beat. Geological time does not set the same rhythm as human time. There are probably infinite sets of time affecting a landscape, depending on how you want to start to break things down. There are infinite beats and infinite rhythms superimposed on one another. They create a music so intricate, we're not able to catch most of it, not even with scientific equipment. I acknowledge time in my process, and I even embrace it as a co-creator. Time is an essential component of my work, but I'm typically ambivalent, even disinterested in time-based media like video, which is the seemingly logical way to incorporate time in visual art. Time in a static image at first seems like it may be an oxymoron, but it's really not. Science does this frequently with graphs. A graph is often an abstracted image of change over time. And many of my projects set up a system that account for time. The systems are designed with a nod toward the scientific graphs. The systems create reference points to compare shifts of color or shape. The pattern of change develops the rhythm of the artwork's composition. Some of the questions that I'm intrigued with about time in my art are, is change the way that we can know time? Is change time, or can there be change independent of time? If nothing at all changes, has time stopped? Time is an ambient static through which we live our lives. It moves forward with the regular beats of seconds, minutes, hours, days, and years, whether we're aware of it or not. It's the space when things happen instead of the space where things happen. Time holds meaning. It's a sense of who we are through our memory. Change is the object that holds the information. And without time, how are we able to decipher the information held within the change? So I'll show you a selection of projects that include time as a prominent component. And Steve, if you have any comments to add from your experiences with your research, please just jump in at any time. This is a year of average colors of the South Yuba River, a mathematical determination of an aesthetic value. It's the first project that I made to be able to see color change in a river over a year. It initially emerged from a sense of frustration. I was living in Nevada City. It's a small town in the Sierra Nevada foothills in Northern California. And I was splitting my time between making art, whitewater kayaking, and teaching kayaking. And that was a pretty good life. I oriented myself to the land by watersheds. And each watershed has its own personality, so to speak. And each river and stream travels through space and time, entering and exiting different facets of the watershed. Nevada City is in the Yuba Bear watershed, and it was due for a 50-year relicensing by the Federal Energy Regulatory Commission, or FERC. FERC relicenses all of a watershed's energy projects, most notably the dams, of which there are many of them in California. The time leading up to relicensing is bustling with meetings with different stakeholders to hash out a plan. Each entity lobbies for the best outcomes for their own interests, some of which include the power company PG&E, the farming communities downriver, the fishing clubs, outdoor recreation, the indigenous Nisenan people. You get the point. There were so many voices just duking this out. It got pretty contentious at times, which was pretty interesting to experience. I attended many of these meetings, as well as scientific presentations about the river. Most of them concentrated primarily on the salmon, or lack thereof, since the salmon aren't able to breach the dams to reach Nevada City. I took the onslaught of relentless data gathering during the relicensing process, and I used it as inspiration to create my own data, data that would never be included in the bureaucratic FERC process. I chose 4 locations on the South Yuba River that held specific personal significance. And every month I returned to the same 4 places, and I took a series of underwater photos, which I then sampled to get my own data, the RGB values of the color of the water. This was another location here. So I averaged the values for each month, and I made a single 7x7 inch monochromatic painting of the average color for each of the locations. And then I averaged each of the locations' color to determine and paint the monthly average of the color of the river. And the monthly averages were ultimately averaged together to determine the average color of the year for each location, and then the average color for the entire stretch of river, which is represented in the lower right panel. So this installation is essentially just an elementary math program, or math problem showing my work to calculate the averages. But a pattern began to emerge with my major projects. The time is a fundamental aspect of each, and to understand the rhythms and spiraling cyclical nature of it, I have to routinely and consistently develop a ritual of being in the land that allows me to develop an embodied relationship with the place over time. I process the experiences sensorially and emotionally, but more importantly, I've collected years of tacit knowledge about these places. And tacit knowledge includes the meaning of a place in a semiotic context, but it also employs memory and imagination, which is essentially what our sense of time is. So my next project that incorporated time to see a dynamically changing environment is called Becoming One Finley. A friend that I knew from kayaking, Sarah Marshall, this is Sarah siphoning water from a piezometer. She was studying wetland prairies and farm fields of the Willamette Valley. And I followed her through her research sites for a year, helping her collect and record data. Learning about real field research data collection was super helpful. But what I found more interesting and what left a really strong impression on me is how she talked about the land and her evolving connection to it that developed through her own regular process of data collection. She had established an enduring relationship to these places that seems similar to what I was trying to achieve with my own art practice. Becoming One Finley tracks and compares the evolving color palette of 2 distinct adjacent fields that Sarah was studying in the Finley Wildlife Refuge, which is south of Corvallis. There's a native wetland prairie, and next to it, there's a farm field that was undergoing restoration to return it to a state that most closely resembles the wetland prairie ecosystem. And this project came directly from the time that I spent with Sarah in the fields, collecting and recording the data with her. I tracked the cyclical color changes in both of the fields for a year. And with this project, I became more aware of how I could orient myself to the place through time, through the color, the intensity, and the duration of light, as well as the colors of the plants in the ecosystem. So I became more in tune to the rhythms of the patterns of the chromatic changes that were happening in both of these fields. So the colors on the left side of the paintings are the most prevalent colors in the farm field, and the colors on the right are from the wetland prairie. Each one of the panels represents 1 month. And now Steve's going to talk about one of these paintings from a scientist's perspective.
So thanks, Leah. I don't know, it was over, wow, we were still meeting in person then, so it has to be well over a year ago. Leah came to give a talk at our monthly H.A. Andrews LTER meetings, and she showed many of these images that you've already seen and others that are still further in the talk. And I enjoyed the images when I first saw them on the screen. They're interesting and they kind of struck me a little bit as well. They're abstract and okay, but as she just described how she did these paintings, I was amazed that her process was identical to what a scientist would do. In fact, if you're a scientist studying remote sensing, you would just be taking pictures with and studying the color spectrum. So what I've done here to illustrate this relationship between what Leah's art does and the science, I've taken a graph from Sarah Marshall's dissertation and graphed it over one of the months of becoming one Finley. And what Sarah's project was looking at was differences in soil properties and how that influenced differences in hydrology between farmed fields, restored farm fields, and the native wetland prairie. So the farm fields are in white and the restored is gray and the prairie's in black. And what she's graphed here is bulk density. So it's kind of the weight or heaviness of the soil. And then the infiltration rate, how fast the water flows into the soil. And the water is on a log scale. So it's like the 2 there means 10 times 10. So that's 100 centimeters per hour. And the 4 is 10 times 10 times 10, and I don't know how much that is. And the 8 is a whole bunch of 10s and too big to write there. So that's why we use a log scale. Right. And so a number of things, kind of jump out at how science and art in this case are so parallel. If you look at the contrast of colors in Leah's painting, you see a huge diversity of colors. Well, if you look at the points for whether it's the wetland prairie or the restored field, you see the points are scattered widely across the graph. And so the location of each point kind of plots it in this diversity of space. No single point is identical to the other points. And you also see an average kind of difference. The wetland prairie tends to be higher on the graph and to the left. The restored ones are in the middle and the original farmland conditions are in the lower right. So we see this idea of kind of a central tendency and the heterogeneity or diversity of the site. And the other thing, stepping away from science and stepping back to Leah's painting, I got to see a couple of these in a gallery. And as I stood there looking at them, they really made me wonder what it was I had been missing. So I looked at the palette of colors that Leah used in her painting, and there were colors there that I completely didn't expect. And I think that's something that's really neat, specifically about art and potentially a science as well, is that by looking at these pieces, it can really challenge our understanding of the world. Art does that perhaps in a different way than does science, but when we look at data and the data are surprising as a scientist, well, how do we explain that? Why does that happen? And one of the paintings that Leah has further in the talk, we'll talk more about this kind of science solving puzzles. But anyway, I just was really amazed by what I saw in Leah's paintings of Finley, and really the sense of I should go back and look at prairie wetlands and see what it is that makes those colors.
All right, thank you, Steve. I have to say that I was actually really surprised about the colors that I got from these places too. If you haven't been in any of these wetland prairies, you really can't see much of what's going on if you're just driving past, which is how I always experience them, because the tall grasses really obscure what's going on in them. And so in order to really see what's happening, you have to go into the fields themselves. And when you go into them, especially in spring, there's just this carpet of flowers that is growing. They're all really, really close to the ground, and there's no way that you'd ever be able to see them unless you went out into the field. So yeah, I found it surprising too. It wasn't just you.
Well, when Leah and I were preparing for the talk, one of the things that she brought up was that, the colors that she got really depended on where she pointed the camera. Which ended up kind of turning into an interesting conversation for us, because it asked maybe something that's fundamentally different about science and art is, what is the role of the artist, or what is the role of the scientist? And in science, we want to minimize the role of the scientist, right? If two different scientists ask the same question and go collect data from the same place, we don't want them getting different answers. Right? That would be really bad science. We don't want to have differences amongst observers. But that's not necessarily so in art. Art is really valuable because the artist adds their interpretation of what they're seeing. So it was an interesting difference, maybe about how art, in a case where the art is actually using a process that's almost so identical to science, and yet they diverge in how they treat their subject matter and the role of the artist versus the scientist.
And I did try to keep this as objective as possible. I knew that nobody would have to actually, replicate my my study, if you want to call it that. But I did try to be consistent, and I found that the more I tried to follow my own system, the harder it was, because I just kept running into more and more complexities that started to really confound me with it. And so that was part of our conversation too. Is just as a scientist, and when you start to, you have an idea and you come up with a method to start studying your site, but then you learn so much as you go into that, and you start to implement your system, and you learn what works and what doesn't work in there. And I had to modify things as I went along, because some things just absolutely didn't work. And so I wanted to know, how do scientists account for that when you get into your process?
Yeah, so that's a real problem, because ideally, right, we as scientists, I think we think there's some underlying reality or a theoretic truth that somehow what we're measuring as scientists is going to illuminate that underlying reality. And so if we choose a method to try and look at something, and as we go along, we continually change our method, then we don't know if our result is simply because we changed our method, or because there's some real difference in the underlying reality of the place or of what's happening. And so as scientists, we have to be super careful. And at the point at which our methods have changed so much that they begin to question our outcomes, we pretty much have to stop and start over. At least if we're good scientists doing good science, we have to stop and start over, say, okay, we were overly naive or overly simplistic when we started out, and now we can devise a better way to do our sampling or make our measurements, and we're going to go back and start over.
And then I definitely started out overly simplistic and overly naive with all of my projects too. But the good thing about what I can do is I can keep that project and then just roll what I learned into the next one. And then, so that's my hope, is that through time, my artwork will become more sophisticated. At least I don't have to scrap everything.
There are some real values in being overly naive, because sometimes by being naive, you will attempt to do things that any person in their right mind with real knowledge would say, you're crazy, that's too much. And people can end up doing amazing things when they don't know they're impossible. So sometimes naivety works well.
And unfortunately, I found myself in that position, starting something that I had no idea what I was getting myself into. But Yeah, that's where
Music.
growth comes from. It's all good.
Yeah.
All right. So this is a project that I did several years after I did Finley. It's called Ambient, and Ambient tracks the color changes in 3 nearby creeks during one fall afternoon. I chose the locations for the creeks' distinct color differences as well as their close proximity to each other. I think that they're all like within about half a mile to a mile away from each other, even though they're so chromatically different. So what you're looking at here is the column on the left. Those are all colors from Watershed 1, which is a steep, small steep tributary of Lookout Creek in the H.J. Andrews Experimental Forest. And then the middle column is from a deep pool in Lookout Creek below a gauging station. And the column on the right is from Watershed 3, specifically in a concrete basin where water and sediment had been trapped. So the bottom of the basin was just filled with this thick brown sludge. And then tannins from the decomposing leaves tinted the water yellow. And what I did was I placed a rock I had painted white in the creeks, and the top row of panels represents the colors present on the rock. So in other words, those are the colors of the water on a white background, independent of the creek bed itself. And then the bottom rows are the colors taken from the creek bed adjacent to the white rock. And then the color variations come from the constantly changing qualities of light and reflection, as well as the variations of the color in the creek through time. This is my white rock in Watershed 1. And this is sound artist Lisa Schoenberg. In this photo, she's attaching sensors to vegetation to record sound. Lisa created a sound piece in Lookout Creek in response to my project Ambient, interpreting my system of collecting the chromatic data to design her own system to collect and interpret sound in the creek. So this perception of time and a place is experienced through memory, and memory holds reference points to perceive change and to sense a unified and cohesive flow of events, like when you're listening to music. So music comprises a multitude of discrete notes played in a specific order. And listening to music requires mental fluidity and memory, holding the sounds and sequences from the past in our minds and integrating them into the auditory experience of the present to experience the cohesive flow of music. There's also the anticipation and expectation that the progression of sound will continue until it reaches its conclusion, extending the perception of the music existing in time into the future. Now I'll play you a short section of Lisa's sound composition. It's called Lookout Sampling Eighth Notes. So this is the Lookout Creek panel, and I believe it's close to where she did her own sampling for the sound.
It's either very quiet or I can't hear anything.
Was that Dominique?
Either very quiet or we can't hear anything.
Oh, that's a bummer. Okay, it's no, I don't know how to change that, so I'll just stop. So that's a bummer that if it didn't come through.
We could, it sounded like just trickling water, very quiet trickling water, something like that.
Okay, well, it's she sampled it, so it's I think she did it underneath. It was in the water itself. I could be wrong on that. And then she sampled it, and so she kind of layers the rhythms on top of each other, and they start to build over time. It's an interesting piece, but I don't know how to fix that, so I'm sorry about that. But the previous project, Ambient, it acted as a prototype for a larger project, Solstices and Equinoxes. And for Solstices and Equinoxes, I returned to Watershed 2 in the Andrews Forest every solstice and equinox for 1 year. I arrived before sunrise to set up my camera, and I used the same white rock as I did in ambient. Beginning precisely at sunrise, I took a photo of the rock, including the adjacent creek bed every 10 minutes until sunset. And this photo was taken on the summer solstice at watershed 2. I used a color checker to be able to accurately adjust each image, so the chromatic reference point for each image would be the same. And then this is on the winter solstice during a storm. The creek was initially low and clear, but as the day progressed, the creek steadily rose and the water became more turbid with sediment, as you can see here in this image. And this is the resulting painting from winter. The 4 light bands in the center of the composition are from the colors of the white rock. The bands slowly dissolve into the pattern of the rest of the creek's colors as time progressed. The sediment load increased the turbidity of the water, making the areas of the white rock almost indistinguishable from the rest of the creek. And then the lighter flecks that look like noise or static, those are from foam floating down the creek and traveling and spiraling through the little pool where my rock was. The foam bubbles increased in quantity with the increasing intensity of the storm. And this set of paintings is from the spring equinox. Every season I set, it was set up with the same system, and the system includes specific acts that must be repeated faithfully for the duration of the entire project. And this unifies the project by creating a structure that eliminates extraneous and distracting information. The system is, it creates a focused, albeit incomplete, interpretation of my experience of a particular time and place filtered through my own perception. The sunrise is represented on the far left. Each column has 40 distinct colors sampled from the same location on my 10-minute interval photographs. I gridded the photographs to make sure that I was taking the color information from the same places each time. And each season's paintings are divided into 3 panels. The smaller panels on the right and the left are the same size in every season's set. So those, they hold 3 hours of colors each. And then the middle panel increases or decreases in size for each season, depending on the length of the day. Then the previous painting, Winter Solstice, all 3 of the panels were the same size. The day was exactly 9 hours long. In this painting, the middle panel has colors from 36 10-minute intervals or 6 hours. So the spring equinox, therefore, was 12 hours long. And one of the things I like about this system of depicting a day is that it feels similar to the local time that we used to be tuned into. I perform the same actions from first light to last light in the same way, regardless of the day's actual length. And in agrarian times, all the days were considered 12 hours, but those 12 hours were relative in length according to the duration of daylight. So sunrise to sunset in winter was 12 hours long, and noon was always determined by the sundial. And sunrise to sunset in summer was also 12 hours long. And our bodies were oriented to natural time according to the duration of light each day, and we filled the day with daytime activities and then transitioned into nighttime activities when the light faded. So on the summer solstice, you can see that the direct light that reached the creek only lasted for a short period of time. The direct light is represented by the light vertical columns in the center panel. And watershed 2 is in an old growth stand in a steep, narrow canyon. And the topography and the forest canopy allow very little direct light to actually reach the creek. Consequently, even on the longest day of the year, or really all through summer, it remains really cool down there all day. So you can see that the colors in the creek are not as varied and vibrant in the summer series as they were in the spring. The water flow in the summer decreased with the lack of rain, and sediment started to settle on the rocks. And then this is fall equinox. The yellow columns represent the only direct light in the canyon, but at this time of the year, the angle of the light was different, and it created reflections of color on the water from the yellowing tree leaves. The white rock in this painting is tinted brownish yellow from the tannins in the water. And that's similar to Ambient's Watershed 3 paintings that were quite yellow. None of the rocks in the creek were visible in the fall. They were all covered with a thick mud from the sediment that the creek deposited in the slow summer flows. So Steve is going to take it from here. He has a couple of slides. So Steve, let me know when you want me to transition to your next slide.
So I was fascinated by this series of paintings from Leah, and to illustrate I think the winter solstice one is the one that best illustrates my fascination, because in many ways, Leah managed to capture just fortuitously a puzzle that hydrologists have been trying to solve for uh, at least a century now. It just turned out that by choosing to take photographs for this project on the winter solstice that year, Leah actually captured the beginnings of the single biggest rainstorm and runoff event of the year. And she was working at one of the rain gauges at the H.A. Andrews, where we collect stream flow data and rainfall data. So I went into our database and I pulled down both the rainfall data and the stream flow data, and I measured them out into 10-minute intervals and then spaced their time so that they would exactly overlap the times when Leah took her photographs. So the bars that hang down, I intentionally left off any scales and numbers here so that it has a kind of an abstract sense, much like the colors that are in the background. But the bars that hang down from the top are the amount of rain that fell in every 10 minutes while Leah was standing out there in the field taking her photographs. And the solid line shows the stream as it rises over the day in response to the rainfall. And you might think it's kind of a stupid question, but the question that hydrologists have been puzzled over is, how does the water get into the stream when it rains? If you look at that kind of right in the middle of the painting, there's one bar that hangs down much further than all the other bars. And if you go straight below it and look at the stream flow, you can see that the stream is gradually increasing, and then you get that 10-minute burst of really intense rainfall. And then the stream flow increases very rapidly for like the next 20 minutes before it kind of slows down, if you will. So it shows that this stream is super sensitive at this point. A little bit of added rain really makes the stream flow increase. And this was the first problem that hydrologists face. They'd go out to the field and observe rainfall in streams, and the streams are super responsive. They rise within hours of the starting of the rain. So a guy named Horton back in 1933 proposed a hypothesis to explain this. And he said, well, the water just runs over the surface of the ground. I mean, it's what you see on your driveway. It runs out your driveway into the gutter and down the road, and away you go, right? Well, some Forest Service hydrologists working in North Carolina spent a ton of time in the field in rainstorms. This was the conceptual model that all hydrologists had about how the world works. And for the life of them, they never saw any water run off the forest. All the rain hit the ground and seeped into the soil. But the reason that hydrologists didn't want this explanation was because they knew how fast water flowed through the ground. And it flows way too slowly to explain the rate at which the stream flow increased. So this is a kind of a scientific puzzle that works just like maybe an art piece that challenges your preconceptions of the world. Right? You have to, well, okay, this is how we thought it worked, but it clearly doesn't work that way. What these scientists proposed was that there was a system of piston flow. And this really seems strange, but it works like your garden hose. If you go out and water your garden on a dry day and leave the hose lay in the yard and sometime later go out to water again, if you have someone turn on the faucet, the instant the faucet gets turned on, water comes out the end of the hose. And that water is hot because it's been laying in the sun, and it takes quite a while before the cold water gets there. So it turns out that soils on the hill slopes work similarly. When the rain falls on the hill slope, it creates a pressure on the water that's already in the hill slope, and it pushes the water out the bottom of the hill slope. Chemists got involved in this story and started looking at the water chemistry. And what they discovered was that actually, and it agreed well with the hydrological theory, that when it starts raining and the streams start rising, all the water in the streams is not the rainfall. It's water that was already in the watershed before it started raining. Hydrologists call it old water. So you have this really weird thing where it starts raining and instantly the streams rise, but the rise in the stream flow is all caused by old water that was already there. Well, chemists continued with some new technologies where they could measure stable isotopes and got better handle on the age of the water. And they discovered that some of the chemistry could only be explained by letting a lot of new water into the stream. So have a fair bit of old water, like maybe 60% old water, but you needed 20, 30, 40% new water. And so that handed a puzzle back to hydrologists to say, well, how do you get new water into the stream? And so the hydrologists came up with a hypothesis that seems to have been well proven now of preferential flow paths, that they're like really big. So the water that gets pushed out by the rainfall on the hill soil, on the hill slope, is all in really, really small pore spaces, but there are larger connected holes that run through the soil that act like drains. And when it rains really, really hard, water gets into those big pores and then they flows preferentially through them just like a drain pipe and takes the new water to the stream. So we can go to the next slide now. So that's what I could see in Leah's drawing of winter solstice. And here I've put the top graph has the bars that hang down, which are the rainfall, and now you can see the numbers there. The line at the bottom is the stream flow, and for winter solstice, you can see how rapidly the stream flow increased as soon as it started raining. And you can see all the other storms of the year, of which there were almost none. You can clearly see that Leah nailed the biggest storm of the year perfectly. And below that, at the Andrews, we collect water over a 3-week period and then analyze it for nutrients and sediment and such. And the samples, the black dots below, show how much sediment is in the water that's collected every 3 weeks. And we must have had some kind of a problem because we ended up not getting a sample the 3 weeks after Leah did her winter solstice piece. And then below you can see the four paintings from Leah all in the same place. And the reason I spent so much time kind of describing this puzzle that scientists face is because this is another, I think at least a really neat overlap between at least some kinds of art. And sometimes art just captures the beauty in the world and it's pleasing to look at. But other times artists really challenge our worldviews, and they challenge them in different ways with different kinds of perspectives. And in many ways, I think if you look at these views of the stream down here that Leah painted, right, it's a completely different view than a scientist might have of the stream, but both of them capture unique things that require explaining and perhaps can change our worldviews, much like the data we collected in these small watershed studies have forced hydrologists to change their understanding of how rain gets into the stream.
I just find that so fascinating because a lot of what you're talking about here is when I was kayaking, I was really watching the stream flows kind of religiously to know when to go out. And at the beginning of the season in the winter time, it would take so much longer after a big rain for the streams to start to rise than it would in the springtime. And that really confused me at first. And so it's so great to have an explanation about what was actually happening, because I could always see it, but I didn't know why that was happening.
Well, it's interesting, right? We have really long, dry summers and the soils get really dry. And these little pores that I described like garden hoses, by the end of the summer, they're all empty. And so the first rainstorms of the fall, you get a little bit of response in the stream, but most of the rainwater goes to filling up the soil. And it's not until the soil is really, really well wetted through and through that the connection between rainfall and stream flow really gets established. And that's the time when the streams become super, super responsive to the rainfall.
Yeah. That's so interesting. So interesting. So yeah, this is just a view of it in a gallery. And I just find that really interesting about going out there and experiencing like that that rainstorm, which that was part of my naive choices as an artist, to go out there and you know, I'll just go out and I'll just sample something every 10 minutes, you know, no big deal. And the first one that I did was that winter solstice, and sitting out in that rainstorm for that whole day was such a miserable experience, and I really did not want to continue with the rest of the project at all. But I had to. And then I have to say, even though summer was really pleasant out there, summer was so long. That just seemed like it was the longest day of my life, sitting out there having to perform the same thing every single, you know, like every 10 minutes. And that was also really grueling for, you know, just the length of time in there. So I have a lot of respect for what you do as a field researcher. It's hard work.
We spend a lot of time, and sometimes in pretty miserable condition, to get our numbers.
Yes.
That we do.
Yes. So I was going to go on with another project, but looking at the time, and it looks like we only have 10 minutes. And so I wanted to know, do people want to do questions, or should I venture on? What shall we do? Anyone?
There are no questions in the chat right now.
Okay.
So
My reaction was, if I had questions and then you answered them as you went along, and you both did it together in a very nice way. So I don't have a question at the moment, but later on.
Okay.
Can I ask a couple questions?
yeah,
So these are beautiful. They really are. And it's very cool. I mean, they're beautiful in themselves, but it's very cool to hear the story behind them. So two things occurred to me. I'm sitting there thinking how practically you actually did the color matching. How did you do that? How did you get your paint colors to be a particular RGB? Like, how did you do that physically? Like, what did you do?
Okay, so I would take the color, the photograph, and then I would adjust everything using that color checker.
Yeah.
This project was actually really hard because the light variation from sunrise all the way to sunset was so extreme that the camera couldn't deal with it. You know, at first I put the camera, I think I was using I don't remember anymore, but I think it was like an aperture value that I was using, but then I would get things blown out or just way too dark. And so I started to have to adjust that during the day just so I can get some information. And then I would have to go back when I was going through all of the photographs. And I had this whole chart with the f-stop values and the amount of spaces that each one kind of jumped. And then I would have to go and adjust all of the images so they had a consistent light value through everything. And so the way that I was looking at it, what I was doing is I was coming up with kind of an absolute value of light and dark through the whole thing. So that was one of the challenges that I had. And then I used the color checker. So I had an accurate color progression through the entire series. And I pulled it into Photoshop, and I used the dropper tool in Photoshop, and that gave me the RGB values, which I then printed. I don't know if I have any of them here in my studio. I just did this whole studio swap, so I don't know where anything is right now. It's like it's too clean in here right now. I don't see anything. Otherwise, I would show you what I did, but I used those RGB values to create these color swatches that I then just, it was all very abstract because there were just like pages, hundreds and hundreds of pages of just color swatches. And then I would mix up my paints and I would dab the paint onto the color swatches until I came up with, as exact of a color match as I could possibly do. But I found that I still had some error doing that. And I actually did another project after this one called Human Error. And that was all about all of the different variations that I would come to, even though I was attempting to systematically mix the same exact color every single time. There were still all these variations.
Cool. Okay, thank you. So the other thought I had is that, of course, the what's being presented here, those RGB values, it's very much a function of the perceiver, right? And in your case, the perceiver is a camera that has a particular sensor array that picks up information. And yes, you've got those color checkers to sort of balance things, but there's limitations on what part of the spectrum the camera sensors pick up. And of course, people build cameras to match human eyes relatively well. But I'm just thinking about, imagine that you weren't a human or a camera created by a human that was doing this, but that you were actually a butterfly that could see into the UV, right? That actually perceived other parts of the spectrum. How would it look different? I mean, this was just sort of I'm not expecting you to answer that. I'm just like, did you think about that aspect of the different organisms in the world would see different different parts of the spectrum with different intensities, and that would alter the views? And could one imagine exploring that? Like that would be
absolutely. Yeah, doing all of these projects got me really interested just in perception in general and our limitations with perception. And so it started just with my own, limitations of perception. And then I started thinking about, what would you actually be experiencing out there compared to what I did? And I didn't expand it to butterflies, but I think that would be super fascinating too. Because it just seems so arbitrary, really.
Well, yeah, I mean, it isn't. I mean, this is the world we live. Not all, humans vary, right? They're colorblind people and people with various color sensitivities, but it does make sense that you're communicating to other humans, and so it's a natural thing. But it's just interesting to just ponder other organisms and how they would like if you had, I don't know what is known about the spectral sensitivities of the perceptual abilities of lots of different species out there, but there's enough variation that you could imagine there might be some really cool differences there.
Yeah, I agree. And if I could figure out how to do that, I'd be really interested in exploring that type of a thing. Yeah. I'm also limited to my own instruments, my own perception and then my own camera also. So I'm always looking for ways to expand this type of a thing to get more information to play around with. So if anybody,
I was just going to comment that you could probably use NDVI sensors that measure false color. That's used a lot in research, and that gives us different images and spectrums outside of the human vision that then get reinterpreted. NDVI.
The problem is under a closed canopy, you won't get it.
Yeah.
So that's it. Really, I think the comment's really interesting about different colors. The other thing that's embedded in these images is time. How would these look differently to an organism who sees time completely differently? A tree versus something, a mayfly who the few hours around the summer solstice are the time that they're out and find a mate and then fall into the water and drift away, and that's the end of their life.
That's another thing that would be really fascinating. If anybody has ideas, throw them my way. This is great. This is really good. I'm actually I'm trying to think of my next big project using time, and I don't know about probably color too. I haven't landed on one yet, so I'm like ripe for ideas right now.
Any other questions? Otherwise, for those of us who are willing to stay on, Leah, you can keep going.
Okay. All right, I'll do that.
I do have a question. Hi, Leah. How are you? Thank you for thank you for your talk. It's super interesting. I was just thinking, wondering if your process of creating art has changed since you kind of became interested in this intersection between art and science. Because what I see from your process, it's that you have a very scientific approach, you know, like where you actually just do observation and like over a period of time and just kind of, analyze, as you said, like you kind of immerse yourself to this space and make sure that you understand it and kind of become part of it and stuff. But I was wondering if before that, your artistic process was very different to what it's now, because I don't know, I'm always thinking about how science also influences art and how art influences science. So, I mean, this is the perfect topic, but yeah, I don't know. I'm just curious about your process and if it has changed.
Yeah, it did change a lot. So that first project that I showed, the average colors, that was a huge departure from what I had been doing before. It was really a side project that I didn't think was going to go anywhere. And so before I was doing work that was a lot more, it's a lot more observation based in the environment. In a way that was more representational, I suppose, to what it is that I was seeing. And then with this type of a project, and this is only, I've really filtered the projects that I'm showing to this specific type of working. It's not always how I work. So this can feel somewhat restrictive, you know, over time, because I have to follow this system over a long period of time, which becomes sort of like a meditation, and there's a lot of patience that's involved with it. But I can't really deviate very much. And so after I finish one of these, then I typically go into a different type of a project that I could be a little bit more expressive and incorporate more emotion into that. And so right now, I'm looking for good ways to integrate more of the emotion, more of the human experience into something that is analytical like this. And I haven't really landed on a good way to combine the two. So the installation over in PV, that one kind of starts to do that. I'm gonna just show that just so you can see what I'm talking about. So this is a permanent public art installation. And it uses the wood anatomy of 4 tree species. And so it follows that pretty closely. And it also follows the data from different forest processes pretty closely. But the way that I integrated the color into this, I wasn't able to do it. I first started to do it like I did with solstices and equinoxes, being really precise about the way that I used the camera, but trying to capture the color from, I'm just gonna zoom forward a little bit. I climbed a 200-foot tall old growth tree every season to be able to see how the color and the light changed from the forest floor up into the forest canopy. And I wanted to be able to originally capture that pretty systematically, but it didn't work out. I could not figure out a way to get my camera to actually have the information that I wanted to. And so I needed to really embed that into my memory and then interpret it later. And so that became more of an interpreted experience that ended up, you can see this reflected color and light coming through in these. That color and light all comes through my memory and kind of the feeling of being in the tree and the changes in the tree as I changed my vertical position in the tree. I don't know if that explains it very much, but it's evolving, and I have these ideas of where I want it to go. I just don't know how to quite do it yet. So maybe I'll do it when I'm overhead. hanging out with you. You can figure out a good thing.
We'll make sure we provide all the tools and equipment that you need in order to do that. But yeah, I think that's wonderful. It actually explains it very well. And it's very interesting how, like, yeah, I can see, I mean, it's interesting that now you go back to memory a little bit of like being in the place in order to create these, you know, like not only the data, but also trying to like what this, like the forest and just being, listening to the trees really make you feel. So, and you're translating it to like with color and stuff. So yeah, it's very interesting. Thank you.
Yeah, thank you. And my ultimate goal is really to develop a relationship with the place. And so just like developing a relationship with a person, you know, there's so much that goes into that. And so it's not sufficient just to rely on, you know, my own, you know, chromatic data or anything like that. I have to allow my experiences and my memory and my perception and emotions to be able to come into these two if I'm really gonna get at what it is that I want to get at. It's it's a big process.
Do you want to tell people what they're looking at in these images if they don't know?
Oh. I don't know. So what you're looking at here is, oh, what was this one? I think that this one, is that the Western Hemlock? Yeah, it's the Western Hemlock. So I don't want to explain this, you know, too much detail because it actually takes a long time to explain what this project is all about. But I went out into the forest with Fred, and we collected, or we tagged these different areas on 4 different tree species to be able to make cookies to then see the wood anatomy from root to the canopy, so the top of the tree. And so this is taken from a chunk of tree that I worked with, and then somebody else did the imaging for me. Down at the bottom is the graph. That is the dendrometer data taken from metal bands that are wrapped around the trunks like belts. They measure the tree's shrinking and swelling diameter. So every time that I climbed the tree, we got data from 2 days prior, the day of, and 2 days afterwards to be able to create these graphs for every bottom edge of the panels. There's 16 panels in all. And I know that you prepared this. If you wanted to talk,
we don't have to talk about mine. We're out of. I think the questions. I think the questions people have is way better. So I can.
Okay.
Yeah. We can skip this.
All right. Okay. So the tree species here over on that small wall, that is red alder. And then the next one that you come across is Western Hemlock, then Pacific Yew, and then Douglas Fir. These are also progress as far as seasons go. I started in spring, so it goes spring, summer, fall, and then winter over on the right-hand side. And then the bottom panels, this is the bottom right here, those are all from, it goes from root to butt flare, which is, it's near the bottom of the trunk. The butt flare is kind of like where you'd hug a tree. And then mid-bowl is where the anatomy comes from. And then the top of the crown is up at the top. You can see the top of the crown there of the wood anatomy. And then the color is infused in there with every season. And the graphs come from air temperature, and those are all the top rows are all from air temperature, and then leaf wetness, then the dendrometer, and then soil temperature is down at the bottom. If that makes sense. So a lot of stuff going on with these panels. Any other questions that anybody has?
Steve, you had good numbers for the size of those tubes going up for Doug fir, for example.
Yeah. So the patterns of holes that you're seeing are the xylem cells of the tree, the cells that transport water. And what Leah's done is she's taken a really zoomed in look. And so each of those little holes is an individual tree cell. And the biggest of those holes is about the diameter of a human hair in real life. And the cells themselves are about 1/10 of an inch long. So our tallest Douglas fir tree in the H.J. Andrews is 90 meters tall. So there'd be something in the order of, I think, 90,000 of those cells running from top to bottom. And they transport water in the tree. So.
That's amazing. Do you know how the water gets transported all the way to the top of those really tall trees?
It basically and really literally gets pulled out by the atmosphere. And that's part of what you see here. In these really tall trees, there's a column of water that runs all continuously from the pores of the soil into the roots and all the way through the trunk of the tree and out the branches to the leaves. And it's a continuous column of water. And the evaporative demand of the air actually pulls the molecules of water out of the leaf. And by pulling so it's like a big chain, and you pull one link of the chain out of the leaf, and the whole chain moves, bumps up one molecule length. And so every time a molecule of water evaporates, the whole thing moves up. And the tree has to be super careful when either the soil gets really dry or the atmosphere gets really dry. The degree to which this column of water is getting pulled on, it's like having this chain being pulled on, and of course it will break at its weakest link. And once it breaks, it creates an air bubble, and then water can no longer move up that column of cells. And if you create enough air bubbles, you'll eventually kill the tree. So they're very carefully evolved to be able to control how much they have the hole that the water exits the leaf through is called a stomate, and the trees can control the size of the hole. And when it gets really, really dry, they close the hole completely so that they don't lose any additional water. Otherwise, the tension on the water column would break it, and then the tree would die of air embolism, it's called. But if it's a really long drought and the trees keep their stomates shut for a really long time to avoid air embolism, they'll die of starvation. They won't be able to fix carbohydrates into sugar through photosynthesis, and they'll die of carbon starvation, basically.
Yeah, thank you.
That was an excellent lesson, and I really appreciate the opportunity to be here and see that. Thank you. And Dominique, I'll send you an email with some further thoughts. All right. Goodbye, everybody.
Bye, Herman.
Bye.
Well, that was
Thank you, everybody. And if you want to see more, well, I think I just stopped. Yeah.
You stop sharing, but that's okay.
Oh, good. No, it's okay. Yeah, that's all right.
Yeah.
But if you want to see more of the projects, you can go to my website, which is my name, leahwilson.com.
Oh, I was just going to ask. Good.
Yeah, thank you very much. That was a great talk and great discussion. Really enjoyed it.
And if you're in Corvallis, all you have to do is walk over to PV Hall on the campus, and you can see those magnificent panels of the wood anatomy that are there in the building.
And also, if you live in Corvallis, every year, at least when it's not a pandemic, the H.J. Andrews has an HJA days, and you can go and visit the forest and see where everything is.
Great.
Yes.
And within a day or two, this recording will be posted on the ArtSci website. So check out ArtSci at Oregon State, and you can see all of the talks that have been given so far are posted, and we'll continue to do that through the series. So if you know of anybody that might be interested, send them that link.
Right, absolutely. And all the talks are also posted on the Corvallis Art Center website. So in case you can't go to one site, you can go to the other and you'll get those recordings. So, and thank you, Jerry, for transforming the recordings into YouTubes.
Well,
I'm finally
thank you.
getting good at some technology.
Yeah.
Well,
you are.
I'd like to say thank you both to the folks who invited us to give the talk, and also to Leah. It's been, for me, it has been, I am married to an artist, but I actually not an artist myself. And it's been really fascinating for me to see the works that Leah is doing and get to think about them. And I love that overlap between the science and the art there. It's been just really fun. Thanks, Leah.
Oh, thank you too. I've really been enjoying our conversations, and I'm really glad that you've just jumped in and done this. It's been fantastic. I want to continue.
There you go. Don't stop. Keep him hooked. Okay. Well, let's enjoy the last few rays of sunshine.
Okay, all right. Thanks
Thank you.
everybody for attending.
Thank you very much.
Thank you.
And
Bye,
see you
everybody.
next week.
Okay, yeah, see you next week.